So what I will do, I will post the third assignment today. This assignment will be from chapter 10, 11, 12, and 13. You are not able to solve this assignment completely, but because now we have very less time, only 2 weeks, I want you to at least start solving those part of the questions which we already covered in chapter 10 and 11, and gradually every day when you cover the chapter, so you can solve the assignment, so you do not need another week to solve that. So when we finish the required chapters for that assignment, so then you will be it will be just one more day and then you can post the assignment. Okay, so today we will cover this chapter 12, context free grammar. We cover first part of this course, which is theory of regular languages, and now we will see how we will use this grammar. We create so far a lot of mathematical models, FA, TG, NFA, GTG, and then another machines which are not mathematic, which are not used to define the language, but you can give the output by Mealy machine and the Moore machine. So we saw all those things. All those things just talk about uh, the valid words or the invalid words. Okay, and now we need to write a grammar for a language to find the mistakes in our mathematical models and in our input. So this is second part of the course where we will see that how we can write the grammar for a language. So what happen when your language, let's talk about English language. So English language by nature is infinite language. So it has set of alphabets, set of characters, set of words. From words you make set of sentences, and you have infinite sentences, and from those sentences you can create anything, any letter, any essay, any kind of English literature you can write with those combinations. So now when your language is by nature infinite, so then how we figure out that this sentence, this combination of sentences, or this combination of words are valid or invalid? So in this case we need a grammar, exactly like we have English grammar. So English grammar will tell you that, okay, this sentence is a question sentence and you should put a question mark at end of the sentence. So your sentence has minimum this architecture. It should have a noun or pronoun, verb, adjective, adverb, full stop. So all these punctuations, all these things are well defined by rules and restrictions imposed by English grammar, and that will help us to validate that whether this sentence is a valid sentence or invalid sentence. So sometimes we have a combination of valid words, but they are not arranged in a way that it make a valid sentence. So like if we have a three words, he is, let's say four words, he is a boy. Okay, so now and then full stop. So this is this, so he and is and a and boy, all these four, and then the punctuation, full stop, all these are the valid words. But if you arrange in these words in a way like boy, full stop, is, he, a, this is not a sentence, it's a mistake. So who tells us, how we know that this is not a valid sentence whereas it is combination of all valid words? So now English grammar tell us that it is not according to the template of the sentence. So English grammar create a template of a sentence. So exactly the same way we have grammar for these languages, which are regular languages or non-regular languages, context-free languages, context-sensitive languages. So we have these grammars, and this grammar we can make some rules and regulations, and that will help us to figure out that whether these are the valid combination of the words, but it's this is, but this is not whether this is a valid words, but whether this combination is valid or not. So are you able, the way you arrange these words, the way you organize these words, is this a valid organization or not? So our grammar will tell us. Okay, so this we will see in more detail in coming chapters. So now when you compile a program, here it says it generate and it perform an operation, it creates a language into the machine language or the assembling language. And the first phase of this is parsing, where you figure out that whether your grammar is right or wrong. So now your language is right or wrong. So now let's see some introduction here, some terminologies. I just explain you that what is grammar. Grammar is motivated with the English grammar. It's a set of rules which the by which the valid sentences in a language are constructed. So when you create your own language, you are free to create your own rules and restrictions. Okay. Once we end this course, I will show you my research work, how I created my non-verbal language, communication language between inter-robot communication and the robot and the human, and then how I impose English, the grammar there, and how I create some rules and restrictions for that grammar. Okay, I will show you that. So now it says that to determine that whether your sentence form is according to the rules and restrictions, we call that this process is called parsing the sentence. That we are parsing that whether this sentence which we just created is according to the rules and restrictions of the grammar. So now when we talk about English grammar, it is composed, English grammar is taking care of two things. It is taking care of the syntax, that whether this syntax is right, this template is right, it is according to the template when we talk about the syntax, and also the semantics, the meaning. So let's say if you I show you one example here. So the Wednesday sings. So now if you see this, Wednesday sings, a bird sings is a valid sentence here. Okay, birds sing. So this is good. So birds can sing. So you can just combination of two words and then full stop, and then you can say that somehow in its nature this is a valid sentence according to rules and regulation of English grammar. Okay, but so now we understand that if this is a sentence, this is a syntax, that we understand that you should have a noun and then you should have a verb there. So when any noun perform any job, it is a verb, and this combination is a valid sentence. And now if you see that we have a noun here which is Wednesday and sings, but this is valid words, valid template, syntax is right, but it is meaningless. Semantics are not right. So English language take care of two things, semantics and the syntax. But the languages which we are talking, which we learn in previous chapters and in future now, we do not take care of semantics. We just take care of syntax analysis. That's it. Okay. So we will not take care of the meanings. Our concern is just the syntax. It is exactly like if you write any code in C language or in PHP or what other languages, Python. So you just take care of the syntax. It never says that you never get this error that, oh, your semantics are not right. Always you get, if you do any mistake, a syntax analysis. Your syntax is not right. Syntax error. So our languages, these non-verbal communication languages, or these English, the programming languages, all these take care of the syntax, not the semantics. And the same is true with our formal languages. So now, when you write a word, the words, so now in this, when you write those rules and restrictions for English grammar is composed of rules. So now I can write this way. There is a rule one. Okay, let me write this. So there is a rule one, rule two, rule three, so on. This is what? This is grammar. All this combination is called grammar. And this individual rule is called, in professional way, we call that it's a production rule. Okay. We call that this is a production rule. So now These production rules, each rule is composed of two things. One is called terminal, second is called non-terminals. So now you understand, you should visualize what we are talking about. So we have different rules. Combination of these rules will create a grammar. Each rule is composed of two things, terminals and non-terminals. Now, what is terminal? What is non-terminal? Anything which cannot be replaced by anything is called terminal. Anything which can be replaced by either terminal or another non-terminal is called a non-terminal. So let me give you an example of this. I need to add a empty slide here so then you can understand. Okay, so we have this thing. Let's go here. So now let's say I have just follow this thing, this example, and we try to write here. So now we are saying that when we have English grammar, it says you should have noun and then you should have verb and then full stop. Okay, so this is a template. This is a template to make a sentence. Let's say this is our one production rule which says whenever you want to make a sentence, minimum you need this, and this is a template of that. Always noun comes in front of that, verb is after that, and then full stop. Order should be like this, and individually our machine will tell that whether this noun is a valid word or not, this verb is a valid verb or not. Our machine will tell that. And how machine will tell that? If that noun or that verb end at, when you do the parsing, if it is end at the final state, we know this is this is part of our machine, okay, our language. So now for the verb we figure out that sings. I replace in second step, this is my first step. In second step, I replace my verb into sings, but noun I replace another two subcategory. That noun can be anything. It can be pronoun, or what are the different categories of noun? There may be pronoun or let's say any other category. Okay, common noun. Let's say common noun. Okay. So now we are saying that let's say we have two categories, pronoun and common noun. So anyone who is so English is your first language, so you should understand. Huh? This is the part of the English language, English grammar. So now pronoun and common noun, and there are a lot of other categories of noun. So now if you see that sing is the final word, which these are noun and verb are non-terminals. And now here, if you see that we replace this non-terminal into sings, and sing is a word. You cannot replace that with something. So this thing is terminal. But here now, you have these two different categories of noun, which are pronoun and common noun. You know that these are not the words; these are subcategories of noun. So you see, this is also non-terminal noun, and I replace noun with another two non-terminals. So these are again non-terminals, and this is non-terminal. This is terminal. Now I say that okay, I put the Wednesday here. Okay, let's say I put the birds here. Birds, bird. And I keep, I got the sayings already there, so I just put it here. So bird sings. So now if you see that this combination has all terminal and terminal. So now bird is a final thing. It is not a subcategory of noun or any other kind of noun. It is actually you replace that thing with actual word. So when you have any kind of this thing which you replace that, this is called a terminal. And now you know that bird cannot be replaced by any other thing, sings cannot be replaced by any other thing. So this is terminals. Anything which has potential to replace by something is called non-terminal. So now and now when we make this sentence, we parse that whether this is according to the in English language, it is according to the semantics, valid semantics or not. Yes, it is good. But if you put instead of bird Wednesday, so it will be invalid word. So now this is basically something, some difference between non-terminal and terminal. Terminal can be, now if you read this, it is written here that that terminals, the words that cannot be replaced by anything are called terminals. Words that must be replaced by other things, what are those other things? Either terminal or non-terminal, are called non-terminals. The job of sentence production is not complete until all the non-terminals have been replaced with terminals. So it says that we cannot say that this is a sentence, that this is not a sentence. This line, pronoun, common noun, or sayings, this is not a sentence until you have a single non-terminal in your sentence. Your production of sentence will not complete. We will not call that this is a sentence. Sentence will be when it is just a combination of terminals. No non-terminals should be part of the sentence. So production will not complete until you have any single non-terminal there. So like now in this case, this is a valid sentence because there is all terminals. Okay, no non-terminals. So this is a valid sentence. So now, guys, whenever you have any questions, please feel free to ask me a question. You can interrupt me. Okay, so don't wait that if you're confused with anything. So now we can see some previous thing which we already learned before, recursive definition of arithmetic expression. So we are saying that these are two rules, and there is a third rule, that there is no other rule than rule 1 and rule 2, and you can define arithmetic expression this way. We have this rule 1 that 3 is, so now we have this, let's say, this arithmetic expression, and we want to prove that by these recursive definition, that whether this is arithmetic expression or not. So we pick 3 and we are saying this is member of arithmetic expression by rule 1 because it says any number is in AE. Then we pick 4 and then we pick 3 plus 4 and the parentheses by rule 2, this thing. So then we have this, we pick 6 and 7 by rule 1, and then 6 plus 7 again by this thing, and then we have two things now, 3 plus 4 and 6 plus 7, and now we consider this as x, this as y, and we pick this thing. So now you see that this is a, by that you can prove that this is arithmetic expression. So you just use all the given production rules, and then given these recursive rules, and you can prove that this is arithmetic expressions. And now let's say uh, so from there we learn that is it possible that we can convert these rules into any program. At that time we have assembly language. We said, okay, let's try to convert these recursive definition into assembly language program. So now if you see that load 3 into register 1, load 4 into register 2, so these are the mnemonics of assembly language. So assembly language has some commands, we call them mnemonics, and these are the basically we use that, and then we combine these two registers, we plus that, and we got the answer of 3 plus 4. Then we load this 6 into another register 7, and then we combine that, we find the answer, and we store that into register 3, and then finally we multiply register 2 and register 3, or register 1 and register 3 to get the final answer. So this way, I mean, you can convert, you can see that you can improvise your these recursive definition into assembly language, that how you can write that. So the grammatical rules are referred to as a production rules. We can see now in more details in coming slides. So now look at this. We are saying that the same thing which you just did, we can write in this format also. So we are saying we can start from this way, because when you have some production rules, you should mention that from which production rule you should start parsing. There must be minimum one start rule, or you may have more than one start rule. but minimum one start rule must be there from where you start, and then you can start parsing or your sentence. So we are saying that we start from here. We have this production rule, and all these are production rules now. And we can say that this whole thing is grammar. Okay. So this is a grammar. So we are saying that if when you start from this production rule AE, then AE, this is a non-terminal. It can be replaced by this thing, and it also can be replaced by this thing, and this way you can apply all these production rules, and this can be replaced by a this way, and AE can be any number. So now here, if you see that in our this production rule, we have this parenthesis and this parenthesis. This is not non-terminal, it is terminal, because once you have this sign there, it is there in your sentence. It will never gone or replaced by anything. AE is a non-terminal, it can be replaced by any other number, but any numbers or any symbols, any mathematical operators, all these are not terminals. Okay, this is another thing. So now we can see some more example here. Uh, so in short, we can say that this is some grammar which will define, which can validate arithmetic expressions, and all these are production rules. Okay. So now we have another grammar here, recursive definition here. We are saying that we have this rule one, any number will be first digit. Rule two, first digit can be replaced by first digit, other digit. And now first digit is 1 to 9 and other digit is 0 to 9. And now from this recursive definition, these are some recursive definition, let's say, we generate some rules here. What are those rules? We want to uh, figure out whether 1066 is any number or not, and it has four digits. Okay. uh, so whenever you want to parse something, you should have a target sentence in front of you and use production rules to generate that target sentence. So we always have this 1066 in front of us, and we need to know that is it possible that by using these four production rules, can we generate 1066? So here we start from this one, any number is equal to can be replaced by this sign, means can be replaced by first digit. So we start from this one, this production rule, and then we have first digit. Okay, and then we know that our first digit is 1. So then we need to replace this first digit by this production rule, because it says that first digit can be replaced by these two things. So we are saying, okay, we have this thing, we replace that with first digit and other digit. Okay. And now we know that we have, look at this one, first digit and other digit. Okay. But we know that first digit can be replaced by any one of this, 1 to 9. Other digit can be replaced by any one of this, 0 to 9. And we need first digit at first place because our letter is 1, it is not 0, and 1 can be come from the first digit. So that's why we use first digit here. Then we but how many these symbols you need? We need four symbols. So then we use, again we repeatedly use this first digit rule two more times to get four digits here. So we said, okay, let's again replace first digit by using this production rule, first digit and other digit. Okay, and we take this other digit down here. Now we have three non-terminals here. We again use this first digit and use this rule 2, and we replace that with first digit, other digit, and we put this thing down here and put this thing down here, other digit. Okay. So now if you see this, we have first digit, other digit, other digit, other digit. Now we have four numbers there. So from this definition, rule 3 and rule 4, we replace first digit by 1, other digit by 0, other digit by 6, other digit by 6, and we achieve 1066 by using this production rule. And this is the valid way of, this is called a derivation. So you derive your actual sentence by using the production rules, and this production rules will tell you that what should come at the first place, what should come at the second place, and you can generate any size of the number with that. Okay, so that's the idea behind that. And the same is case here by this one, by this thing. So you can have, you can start with S can be replaced by AE, and then AE can be replaced by using this production rule into this thing, and finally this, and finally you have this final sentence in front of you, and you use production rules accordingly, which will lead you successful generation of your sentence. Okay, sometimes you have invalid sentence which is not according to the template, and you are not able to generate that. So let's say I give you one example. If I have a word 0166, I am not able to generate that because uh, it always says that you always have first digit at the first place. You will never have other digit at the first place. Okay, because this is the only rule here. So now if you never have other digit at the first place, there is no way you can replace, you can generate this zero at the first place. So you always, you can have zero but not at the first place in your sentence, somewhere in the after the first place. So if you have 0166, you are not able to generate this word by these production rules, by these production rules you are not able to generate that. So you only able to generate any word which has zero not at the first place, at the starting of the sentence, somewhere in between or end. So this is a restriction for this grammar, let's say. Are we good? So Riley, are you happy with this? Okay. So if you have any questions so far, I can help you. And so Nikhil, so far, do you understand terminals and non-terminals and the production rules, grammar?
Yep.
Okay, that's great. Okay, so guys, please don't hesitate. So ask me a question. Okay, so if instead of going forward, I can help you right away if you confuse anywhere. So Riley, do you think if I can, where you confuse, so I can revise that concept? So yeah, I guess combining the rules with the first part, combining the rules with the first part. So you mean uh, when you say the first part, what do you mean by first part? So this thing that how we write these rules, so this part. Okay. So this is given. So this is given. You don't need to create these things by yourself at this stage. At this stage, rules are given to you. When you create your own grammar, then you should understand that how I should create. Because okay, let's say I give you one example. I need to create a robot, and robot has two arms, and I just make my own restriction that if robot one arm is right arm is raised up, so and then after that I give this command raise both arms, this should be invalid command because one arm is already raised. How robot should raise both arms? So in this case it should be invalid, and then first robot should lower down the right arm, and then if I give this command raise both arms, then robot should raise both arms. So this is one kind of condition which I self imposed on my language, and then I can create a production rules. in which I generate this way that once you have raise your right arm or raise your left arm command is inactive, I mean active. So after that, if you give raise both arms, it should be invalid command. So how I manage this? By writing the production rules. So this is something I need to create by myself. How I create that? So this is we will see, and then how we create this grammar we will see. We will learn now in coming chapters that how we will create this grammar. So yeah, this is, don't worry about this is your valid concern. I did not address that at this point. After this discussion, I want you to understand what is terminal, what is non-terminal, what is grammar, what is production rules, syntax analysis, and how you use given production rules to derive the sentence. That's it. If you understand this part, job is done. How to write a grammar? This is I did not teach that yet. So now, when once we done this, so let's go to the next slide. Let's see the formal definition of this thing. What we just covered. We are saying that we have a context-free grammar. We call this a context-free grammar. It is combination of three things: an alphabet summation. So now whatever the previous knowledge you have, we will use that knowledge here. So we saw that summation is equal to some a or b. So now you can have more than a or b, and this is your alphabet summation for use for your input letters. All these summations are your terminals, okay, from which we are going to make strings that will be the words of a language. Second thing, a set of symbols called non-terminals. You must have minimum one start symbol which can be referred by s, symbol s, and it should be called as a start symbol. You may have more than one start symbols. Then we have a finite set of production rules, and it should look like in this format. So you should have one non-terminal and then finite string of terminals or non-terminals. So this should be your shape of the production rule. So now, where the strings of terminals and non-terminals can consist of only terminals or of only non-terminals or of any mixture of terminals and non-terminals, I already explained that terminals cannot be replaced by anything. Non-terminals can be replaced by anything. Either it is a terminal or it is a non-terminal or it is a combination of terminal and non-terminal. Anything. It requires at least one production rule which has a start symbol S, and that's it. So now there is another so now this is something which you understand. Another identity, how you figure out in this grammar which one is terminal, which one is non-terminal. Your terminals are always be in small case, lowercase. You will never see a letter, a word in capital case. Always your terminals will be in small case, lower letters, and terminals will be combination of lower letters, signs, mathematical signs, symbols, parentheses. All these are comma, plus sign, minus sign, star, parentheses, star, slash. All these are, and the small letter. All these are terminals. Anything which is written in capital letter, that's it, just capital letter, it is non-terminal. This is a big identity to figure out the differentiation between terminals and the non-terminals. This is very important. Okay, this is another thing. And now a sequence of applications of productions starting with the start symbol and ending in a sequence of terminal is called a derivation or generation of a word. So the language you create by context-free grammar, we call it in short CFG, is all the combination of strings of terminals that can be produced from the start symbol S. So using the production as substitution, we call that we define the language, we derive the language, we produce the language. So now another thing, when you talk about context free grammar, this grammar define which language? It define context free language. Okay, so context free grammar is used to define the context free language. So this is another important thing. And now context free language, yes. And now we will see these the practical examples of those what we learn, and you will be better positioned to understand the terminals, non-terminals, and the production rules. So let's see, we have a grammar here, and this grammar has two production rules. One, two. And these two production rules, if you see that it has, both are the start production rules. How we know that both are the start production rules? This thing. Okay. So both are the start production rules. And then you can see that these start production rules so we have two production rules, both are the start production rules. How many non-terminals we have here? All capital letters. So we have capital S, capital S, capital S. We do not consider same thing two times or more times. Same thing we only consider one time. So we have only capital S in this. So we have only one non-terminal here. And how many terminals we have? Any sign, symbol, or small case letters. So you have small a here, and that's it. This is your terminal. Lambda is not a terminal, is not a non-terminal. Okay, we will see that why this is a case. So we do not consider lambda either terminal, either non-terminal. So now when we have this grammar, which grammar has two production rules. Okay, another big identity of non-terminals, you will always see you will never see any terminal on the left side of the production rule, because if you see this, what does it mean? S can be replaced by AS. S can be replaced by lambda. So you will never see, because terminal cannot be replaced by anything. So you will never see terminal on the left side of the production rule. Always, all production rules must be on the left side. They can come on the right side also, because non-terminal can be replaced by terminal or non-terminal. So, but you will never see terminal on the left side of the production rule. Okay, so now we have this word in front of us, and we want to generate that by this grammar. We always keep the target word in front of us. We can, so now these both are start production rules. We can start from anyone. Here in this case, if you start from this production rule, you know that this will not, it has lambda. Lambda cannot be replaced by anything, so you cannot able to reach to the successful generation of this word. But you can start from this production rule, and now I said, okay, I choose this one. S can be replaced by AS, and I repeatedly use this production rule again. S can be replaced by AS, AS, AS. I have 6 AS here, and then I replace. So now it is my choice. Either 6 time I use this production rule, or I 6 time I again use this production rule, and later I replace S with lambda. It is again it completely my choice. The way I want, I can choose that, and I generate this word. And now, if you see that if you see this grammar here, we can see, we can figure out that by this grammar, you can have lambda, you can generate one A, and then S can be replaced by lambda. You can generate 2 A's, and then S can be replaced by lambda, 3 A's, then S can be replaced by lambda, and so on. And what is this? This is basically A star. So we can say that this grammar define this language, A star. Okay. So I saw some question here. So does the choice of which production rule always come down to the user's choice? Exactly. It is you who will know that at this stage, you will choose that. But later at this time, we are generating the grammar, we are learning the grammar, how to create that. So that's why we can do this way. But very soon you realize it's a big headache when you do not have any certain order or rules that how you use this production rule. So then our first job is just try to understand how to create a grammar and what is grammar. In the coming chapter, we make some rules, some restrictions to make a clean grammar. So we will have ambiguous grammar, we will have unambiguous grammar, we will how we use these production rules to generate that generate the word. how machine knows that which production rule we should use, how machine knows that you have something like this, let's say a, oh man, a capital A capital A. How machine knows that which non-terminal it need to replace now. So it is big ambiguity. You have lambda there. How machine take care of lambda? So there are a lot of problems with the grammar at this time. We do not take care of that. At this time, we just create a grammar. Later, we clean the grammar and we make grammar more readable and more autonomous, that it does not require human wisdom, human input, and machine automatically parse your sentences by using that grammar. So later we will do that. This will be, you will do this very soon in coming chapters. But at this time, you are right. Choice of the rule is based solely based on the human choice. Okay, so now we are, so do you understand this thing, how we get this A star, how we can say that this grammar belongs to A star? Any question into this one? If you guys have any question, how we figure out that this is A star? Okay. So if you are happy with this, so then let's go to the next step. Another example. So now this example, how many production rules? We have three production rules. How many non-terminals? Anything on the left side, S. How many terminals? Small letters or the sign and symbols? Only A. You have only A as a non as a terminal. So now you want to generate a word which is AA, let's say this word. So you have three production rules. You can start from any one. Let's say I cannot start from this production rule, because if I start from this, and then what, how I replace this lambda? Nothing. So I cannot start with this one. I can start with the second one. If I start with this, how I replace this A with anything? A is a terminal. Terminal cannot be replaced. So you are not able to replace that. Yes. So there is no way. So you cannot start with this one, this production rule. Let's say I start with this second one, S, and I say that yes, now this is non-terminal. You can replace this S and this second S with anything else. So I said I replace this first S with A, and then I have S, and then I replace this AS into A, and then S can be A, and that's it. I can create A here. Or you can choose this way of derivation. This is, I mean, SS, and then replace this one S again with SS, and then again this S with A, and then replace this S with SS, and then replace the first S with lambda. Just, it's a long way, just to show you that you can choose, do whatever you want to do. And then this S with A, and then this S with lambda, and then lambda concatenate with any letter, it will vanish, and you will have A there. Okay. So these arrow means can be replaced by, and this double arrow means can develop into. So we have this grammar. It is doing something. Looks like it is creating A star, and it is composed of three production rules. So you can have more than more than one grammar to define the same language. So we have this grammar with two production rules to define language A star. We have these three production rules to define the same language. So you can have more than one grammar for the same language, because you can have more than one regular expression for the same language. Okay. So now let's talk about lambda. Why? What is this? So now is it a non-terminal? No. Why it is a non-terminal? Because lambda, what is the property of non-terminal? That it can be replaced by anything. Lambda cannot be replaced by anything. You cannot replace lambda into A or lambda into B. So it does not have the property of non-terminal. Okay. Is lambda a terminal? No. Terminal cannot be replaced. Terminal cannot vanish. Once you have any terminal there, it should stay there. But now look at this one. You have lambda. Lambda can concatenate with AA. It will vanish, and you have no lambda here. So lambda does not bear the property of terminal. So it does not have the property of non-terminal or terminal. So it is not terminal, either it is not non-terminal. So lambda n can, so like this kind of production rules, n can be simply be deleted. So it is nothing. So we just say that we have lambda production rules in our grammar, but lambda is a third kind of thing. It does not qualify either in terminal category or non-terminal category. Why? I just explained that because terminal, it should stay there. It can vanish because lambda concatenate with anything. Non-terminal, it can be replaced by anything. Lambda cannot be replaced by anything. So it does not have any property of that. Now, some more rules, some more grammar. We have this grammar here, and it has four. Let's talk about this one. So it has four production rules. 1, 2, 3, and 4. Four production rules. And how many non-terminals? Just one non-terminal, S. How many terminals? Two terminals, because two small cases, A and B. So look at this one. So I write this thing here. So we have two terminals, A and B, and you want to generate B, A, B, B with that. So let's say, or A, B, B, A. So any word, let's say we have this word. So we can generate that. We start with any production rule, but we start with AS, and then S can be replaced by BS, and then S can be replaced by again BS, and then S can be replaced by A, and we generate the final word what we have in our mind by these production rules. So this process is called a derivation process. Then we have another grammar here. It defines some other language. It has some more production rules. Look at this one. So now how many terminals we have? We need to see the small cases, A and B. So we have two terminals. We don't consider the same terminal used with again and again, two times or three times. We will say that this is one terminal we use again and again. So we use small a and small b in this grammar as a terminal. How many non-terminals we have? We have S, we have X, we have Y, and look at this one, X, Y, 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 Y. All these are SXY. You just consider these non-terminals one time distinct. Do not repeat that. So we have three non-terminals, S, X, and Y. Okay. So these are, you see, all non-terminals are capital letter, all terminals are small cases, all non-terminals must, it should be on the right side. It can be, but for sure it will be on the left side. So it's very easy to find the difference between terminals and non-terminals. So all the non-terminals are on the left side of your production rules. You can easily see that. And which grammar? It is A plus B whole star. So if you notice here that by these production rules, can you generate lambda? Yes, by this one. You can start, S can be X, X can be lambda. Can you generate A only? Yes, by this production rule. S can be X. How we generate A only? Oh, here. S can be Y, and Y can be replaced by A. So you can generate A. Can you generate B also? Yes. S can be Y, Y can be B. Can you generate A, B? Here, S can be Y, and Y can be A, Y, and this Y can be B. So A, B, B, A. So this is ongoing. So this is A plus B whole star. So you can generate anything with this thing. This is infinity language, okay? But this is a regular language. You see that? So you can generate uh, this grammar here. So now look at this one. Another example here. So it has S, only one non-terminal, A, B, two terminals, okay? And this also, so now we have, we reduce this grammar into here. And how many production rules you have in this grammar? 1, 2, 3, 4, 5, 6, 7. Here now we have 1, 2, 3, 4, 5, and it is also generating lambda A, B, A, B, B, A, B, B, everything. So this is again the same language, but less production rule. So more intelligent grammar for A plus B whole star. Okay. So now look at this one. This is the new grammar which only has three production rules. it also all these three grammar represent same thing. They represent the same language, but the last one is more intelligent. It has less production rules, means less resources, and you can define the same language. So all these are defining the same language. Okay, so we will learn that how we make right the intelligent grammar, how we achieve this. We will see that in coming chapters. So the first example is a plus b plus a plus b uh, positive closure. It gives you a or b. Yes, yes, you are right. A plus b. You are right. Yes, it is. It is something like this. Yes. It looks like that. You can have A, you can have B, you can have A, you can have A B, you can have B A, you can have B B. Yes, you are right. 100% you are right. It is A plus B plus sign. It is a positive closure of summation is equal to A comma B. So it's very nice, Riley. You are thinking very good. But the other three are A plus B whole star, clean star. It's very nice. You can create, you can fill this grammar by like this, and you can figure out that how it is. So do you understand that how this is positive closure, Riley? We can get lambda. Yes, yes, perfect. This is very nice. So now let's see more example here. So we have this grammar in, and this has one, two, three, four production rules. Non-terminals are S, X, and terminals are A and B. Okay, and you can generate any word here. Now look at this one. You can have this grammar gives you guarantee that because you are forced to always start from the start production rule. So how many start production rule we have in this grammar? Only one. This one. We don't have more than one start production rule here. So in this case, if you have not more than one start production rule, so then you have to always start from this production rule. And when you always start from this production rule, just a minute, this production rule, so this gives you guarantee that you can always have 2a must be there, because you can replace x with anything, this x with anything, but these a's will always be there. So it means that, and now what is x? X can be ax, you can start with a, you can start with b, you can have lambda. So it means that it has anything can come in start, anything can come after that, but you must have two a's must be there. So this is the regular expression of this language, and this is the definition of this language. So this language gives you guarantee that whatever the word or sentence you make by this grammar, you must have two a's somewhere, consecutive two a somewhere in your language. Okay, so this is basically this grammar. Right. So now let's see the second grammar. So it says how many production rules, start production, how many total production rules you have? One, two, three, four, five, six, seven production rules. How many start production rules you have in this grammar? One, this one, start production rule. Because start production rule must have start symbol S. How many non-terminals we have in this grammar? S, X, Y. So we have three non-terminals. How many terminals we have in this grammar? A and B. So two terminals. So now, so if you have more than one production rule which can replace the same non-terminal like this or like this, you can, in short, write these in this format also. S can be replaced by XY. X can be replaced by AX or bx, or A. So A, and then Y can be replaced by YA, YB, or A. So when you see something in this case, it is not three production rule. It is again, you can see that it is S can be replaced by XY, X can be replaced by AX, BX, or Y can be replaced by, this is OR sign, YA or YB or A. So this is again total, you have 3, 3, 6 and 7 production rules. But you can write in short in this way also, so it is the same thing. So sometimes people confuse that we reduce that into 3 production rules. No, this is not 3. This is again the same number of production rules, but you write in this way just to look nice and more easy to understand. Okay, so this is basically your another way of writing the grammar. And now we have this example here. We have this grammar. So it has, again, you see, I want to emphasize on non-terminals, terminals, production rules. So it has 1, 2, 3, 4, 5, 6, 7, 8, 9, 9 production rules. Okay. And how many non-terminals we have? S, B, and U. So we have 3 non-terminals. How many terminals we have? A and B. So we have 2 terminals, A and B. And then how many starts production rules we have? 1, 2, 3, 4, 5. 5 start production rules. So this is your another grammar. And if you see that this will be, it is more complicated. So it is something to represent this language, even language. And then you have another grammar here, which is ASB. So it has 2 production rules. Both are start production rules. It has only one non-terminal S and 2 terminals A and B. So this is your non. So now your grammar can represent not only regular language, but it also represent non-regular language. So if you see this, so you want to generate this word. So 1, 2, 3, 4, 5A and 5B. So you start from here, ASB, and then replace this S with this production rule again, ASB, 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 and finally you replace this S with lambda, and you have 4A's, 5A's here and 5B here. So this is your ANBN. So we do not have regular expression for this language, but we do have a grammar for this language. So it means your context free grammar have a big scope. It can be used to define, to represent regular languages and non-regular languages. So it can represent both, either regular and non-regular both. Okay. So your context-free grammar has a big scope. You can use that to define your regular and non-regular languages. So this is the grammar for non-regular languages. So now look at this one. This is your palindrome. So use the way you write from right to left, the same way you read. So this is the production rule of that. So 3 rules, 3 start production rules, 1 non-terminal S, A and B, 2 terminals. Then you have this parse tree. So once you have this grammar, so you can convert your grammar into the parse tree, into the tree form. And if we are able to convert our production rules, our grammar into the tree, we are on the highway, because you know that we have very strong data structure which can deal with binary trees, complete trees, or different forms of trees. So we have very strong data structure. We know that how we traverse in the trees, how we add any node into a tree, how we delete any node into a tree, and how we edit any node into a tree. So this is something very mature data structure, and then easily you are able to traverse everywhere in the grammar. And let's see, are we able to convert our tree into the parse tree, our grammar into the trees? Let's see. So we are saying S can be replaced by AA. So first production rule, AA can be replaced by, so now this can be replaced by either BA, and then actually you have this word here in front of you and you want to generate that. So this A can be replaced by BA, and then this A can be replaced by this production rule. And later you replace those non-terminals, whatever suits you, to generate this word. And finally, if you read all the leaf nodes, you can see that all the leaf nodes are basically your final word which you want to generate, and you read from left to right. So B, B, A, B, this is a word which you want to generate. So when we convert our grammar into tree structure, we see that all the non-terminals are either parent or the or somewhere in between the tree, but all the terminals, when you say that I done my production process and this is my final word or sentence, you will never see any non-terminal at the leaf level. All the terminals will be at the leaf level. So your all um, nodes are which or the leaf nodes must be terminal. If your all leaf nodes are terminal, there you can say that my process of uh, creation of the word is finished. Okay, so now we are saying that, let's see, also called syntax tree, generation trees, production trees, or derivation trees. It's both are the same name of this thing. In a parse tree, every I just explained that every internal node is labeled with a non-terminal, and every leaf is labeled with a terminal. So every node labeled with a non-terminal must have a children. So there is no need to put arrows because we always traverse in the tree from top to bottom. So you don't need to put arrow here because this is the by default understanding. When you're talking about tree, it is its direction is downward from top to bottom. So you don't need to put a arrow in this direction. Okay, it is common understanding. So let's say we have this grammar here. So now this is complicated. How many production rules we have here in this grammar? Gunnar, how many production rules we have in this grammar? Gunnar, are you there? Jacob, Morris, how many production rules we have in this grammar? We cannot hear you. So how many production rules? Jacob, I cannot hear you. How many production rules we have in this grammar? Five rules. One, two, three, four, five. Nice. James Evans, how many non-terminals we have in this grammar?
Um,
So what is the
three?
how what?
Would it be three? Because three out of the five rules are non-terminal.
So I can write here. So we have. Let me write this. We have five five rules altogether in this grammar. One, two, three, four, and five. Okay. Oh man, when I do this, it match with that. Okay. And how many non-terminals we have in this grammar? So, can you tell me the name of that so I can write it?
Um, we have S in parentheses.
No, princes are not non-terminal because you cannot replace princes with anything else. Remember, I told you signs, symbols, mathematical
Oh,
operators,
okay.
small case letters, everything is terminal. So we have only one non-terminal S. That's it. Okay. And beside you,
Okay.
another thing is you never see terminal, non-terminal. You must see non-terminal on the left side. You don't. So in this grammar, you don't see the parentheses on the left side. Yes. So you cannot because you cannot replace that. So how many terminals we have here? Kevin, how many terminals we have here? Nikhil, how many terminals we have here?
Is it three terminals or might because P and Q I believe are terminals.
P and Q.
And then are the symbols also terminals? So like the
Yes.
parentheses.
Yes.
Then would the tilde also be a terminal?
Yes. So one, two, three, four, five, six. Six terminals. Make sense? So we have six terminals. Okay. So terminals will be always on the right side. It can be combination of small case letters, any sign, any symbols, parentheses, mathematical operators. All these are terminals. So I mean, if you see that these, so you if you have parentheses or the sign, you cannot replace that with anything. This is final thing you have. But which is in anything which is in capital letter, which is non-terminal, so you can replace that with something. So this is basically the definition here. Anyways, so now this is good. You guys understand that. Now if I want to generate this word here, look at this word. This is my sentence or word, whatever you want to call. I how I have all. So now another question: how many start production rules we have here? Right, Quinton. How many start production rules in this grammar?
Start production rules?
Yes. This is my grammar. It has five rules. How many start production rules we have? From which production rule we should start?
Uh, two?
This one.
Wait, I don't know. I don't know.
So when you have this thing, what does it mean? So when you have this thing, what does it mean? This thing. This grammar, we write this in short. So what does it mean? It means that S can be replaced by S. S can be replaced by S subset of S. S can be replaced by tilde sign S. S can be replaced by P. S can be replaced by Q. So that's why we have five production rules, because all have the same non-terminal, so we can write in this form with the or sign, but it is same thing. So now, are you able to tell me now that how many start production rules we have here in this grammar?
I'm not sure what a start production rule is.
So start production rule is that production rule from where you can start the parsing, and it how you identify that this is a start production rule. Its non-terminal is S on the left side. So if you have something like this, so it means that you can start from this one. So let's say you have 1000 production rules. So how you know that from which rule you can start? So you always start working from the start production rule. Exactly when you have an FA or TG or NFA, you have a start state. From which state you should start? You have 1000 states. Which state you should start? You should start from looking at the start state. So it's exactly the same way you can start from the start production rule. And how you know that this is a start production rule? It has S here as a non-terminal on the left side. So how many start production rules we have in this grammar?
Three.
Are you sure? Three.
There are three rules which have an S on the right-hand side.
I'm not talking about right hand side. I'm talking about I just explained that the start production rule must have S on the left hand side.
Oh,
So I
okay.
mean, so let's say if I have this production rule, capital A can be replaced by parenthesis S like this. So this is not a start production rule. Start production rule means you should have S here. Okay. So how many start production rule we have here?
Five.
Very good. So we have five start production rules. So then here now we have five start production rules. So then you can change. you want to generate this word. This is target word we have in our mind, and we just create a tree. We can start from anyone, but we start from the production rule which suit us, which we think that lead us to the successful generation of this word. So you can see that I start from s can be replaced by this one, and then this s can be replaced by this. And finally, if once you completed everything, if you see all these child uh, leaf nodes, you can see, actually not this way. If you see all these leaf nodes here, so this will be combination of your final word or sentence, all the leaf nodes. Okay, so now if you write in chronological order from left to right, you can see that it will generate this word. So this is your word here. But now you understand this is painful, when you have no idea that which non-terminal. So now here, if you see, I replace this s into this one, and then I have two s here. So which s I should replace, this one or this one? And then here I have, so sometimes it is very hard for you to figure out that which non-terminal you replace if you have a big grammar and you can generate the desired word. So in this case, you figure out that this is not some at some stage when you have, it is possible when you have 5 to 10 production rules, but let's say we are talking about 100 production rules or 200 production rules, and this is not very uncommon that you have that much production rules. So then it will be very hard as a human being to do that with the naked eye, that which rules we should use and lead us to the successful generation of the word. So we need an algorithm for that. We need a process for that, a deterministic approach for that, that which will always work blindly in one way, and machine can do that, and it can generate your desired sentence regardless how many production rules you have. So this is something now, the challenge which we are facing so far in this grammar. Let's see another example here. This is your another example. It has one, two, three, four production rules. It has three start production rule. It has s and number as a non-terminal. It has one. It has parentheses, plus sign, close parentheses, star sign, and all the numbers. These are the non-terminals, and you can generate any word with that, and you can parse a tree with that. So now if you see this, so you can have, if you have this thing, it has different tree. If you have a different arithmetic expression, it has different tree. It is accordingly, so you can generate that. It's good. So I mean, you see different grammars and you can generate tree for that. Now, so how much we left? Okay. So now once we generate this tree here, so you can see that evaluate expression by starting at the bottom and working way up to the top. Replace each non-terminal by the result of the calculation. So now if you see this, we have this grammar here. We have a, let's say, grammar, and we have a production rule, which is grammar, and we convert that into a tree. And now we want to solve that. We want to figure out that what is the answer of this arithmetic expression. So what is rule of that? So replace its immediate non-terminal with its terminal. So immediate non-terminal for this s is 4 and this s is 5. So we replace that. If we get this second step here, 4 into 5, and in this line you have no non-terminal, just terminals, because all numbers are also terminal. So you can solve that, and you do this on the priority basis. Start from the bottom and go to the up. So 4 into 5 is 20. So you solve that, and then again here, so if you see this, you convert this 3 into s can be replaced into 3, and this way. So you solve that here. Now 3 into plus 20 is all combination of terminals, no non-terminal here, and you can find the answer here, 23. And let's say we have this another tree here. We replace this s and this s with 3 and 4, and we got this one. We solve that, which is 7, and then we replace this 7 by s with 7, and then 7 into 5 we have 35. So You can solve that by this way also, um, for the trees according to the priority. And if we see that, let's say we have, when we convert this grammar into this form, so how we are doing this, how machine can do that. So it is very easy. It is called a Lukasiewicz notation. It's a Russian scientist. Its name is Lukasiewicz notation. So you have a tree here, and you replace the immediate non-terminals with its respective leaf terminals, which are at the leaf node, and you convert your tree into this form. So S can be replaced by 3, this S can be replaced by 4, this S can be replaced by 5, this S can be replaced by star, and look at this one. So this star is here. So now you convert this into this S can be here. So 3 plus, so this star goes here, so plus a star. So you convert this tree into this form, and then you start scan that from top left to the right. So you start scanning that. So you flatten the tree. So you start scan here, and anything come on your way. So you can write that plus 3 and go back. This already visited. We already visited this node. So we do not rewrite this again. And then we come here. It's a new thing. Star 4. Go back. Star again. We already visited that. 5. Go back, star, we already visited, and come back. So this way, so you flatten the tree. So we flatten the tree, and we write this thing in form of this form. Okay. So now we try to understand this here. So we have this tree, we convert that into in this form, and then we start reading from the left side. So how what should we star plus 3, we go back, we already visited plus 4, plus visited, star visited 5, go back, star visited, and we finish here. So this way you can flatten your tree into this form. Okay. So once you flatten your tree in this form, then Lukasiewicz notation says we have an algorithm. What is that algorithm? So let's say we have this tree here, and first I will flatten that, and then I will apply an algorithm on this, and we can solve this tree with the operator precedence. Okay. So now this method will help you to solve it by operator precedence, because you know that operator has the priority. So we will solve this accordingly. So now we flatten this S star plus sign star plus sign star. Look at this one. So you need to read this. So star plus sign plus 1. So we go back, star plus we already visited. We do not write that. Any node which you visit, you do not write that again. Non-visited nodes, you can write that. 2, come here, visited plus sign. 3, visited. 4, visited plus visited. 5, new node, come back here, plus again visited, and then star again visited. 6, new, come back here, star visited, and we finish here. So this way I flatten this tree, and I write this thing here. So once you flatten your tree, every time your job is to scan from left to the right side and try to find this combination: operator, operand, operand, operator, operand. So we are looking here. So it is operator, operand, operand. We find this one: operator, operand, operand. So we solve this. So this means plus 1 2 means you need to apply this operator on these following operands. So 1 and 2 should be plus. So we have 3 here. Once you've done that, so then again start pre-order. Yes. Pre-order tree traversal. You are right. And then we again start from the start. So you do not continue this. Once you find this combination, your scanning should be again start from the first node. Do not continue this. Again start from here. Every time, so initialize again from here. Okay. So we again start from here. So operator, 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 operand, operator, operand, operand. So we find this combination here. We solve this 3 plus 4, 7. So we again start from here. So then operator, 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 operand, operand, we solve this. So 3 multiply by 7, 21. We again start from here. Operator, operator, operand, operand. So we solve this. 21 plus 5, 26. And operator, operand, operand. We solve this 156. And this way you figure out that if you have this arithmetic expression, which you convert this into the tree form, and then you can flatten the tree, and then you solve that by applying Lukasiewicz notation, and you get the final answer 156. So this is very important. I will ask you these kind of questions in quiz also, in exam also. Okay, I will give you a tree, and you need to flatten that and solve by looking at running this algorithm, operator, operand, operand, and then you will find the final answer of that tree. Okay, so I might ask you this in quiz also, in exam also. So any question, guys, here, if you have any question, how we solve this Lukasiewicz notation? It's linear. So when we say computationally expensive, Riley, we need to see that if the job which we are performing, is it a linear job or is it non-linear job? If it is a linear job, it does not involve exponential time work. So then I believe that it is not expensive. So, I mean, with respect of algorithm design and analysis, if it is linear, so then it's fine. It is not very expensive. So yeah, that's the answer of this question. So you need to figure out uh, that. So I mean, point is that when you write the algorithm for that, so write an algorithm in a way that you do not encounter exponent there, because with the definition of algorithm design and analysis, we always prefer anything linear. But if so, linear is our first priority. But sometimes if it is not linear, we can compromise on exponential. This is still not bad. But if you have something like this is very bad. We don't like that. And factorial and other things are for sure, those are not bad. So this is very bad, and factorial is also very bad. So we don't like that. So yeah, so you pick. I believe that this is linear, or maximum it will be exponential, x raised to power 2. So it is not 2 raised to power x. So it is not that bad. But it solve a purpose. The idea is that once you have the algorithm, so you can improve the algorithm. You can get the same job by improvising the code in a way that which will be less expensive. So then we can figure out. That's another job. First job is, can we do that or not? Yes, we can do that. Second job is how we can do this better way. So that is another job. So now we have this thing, and then let's see this example here. So now if you see this, we have this grammar here. S can be replaced by A can be replaced by B can be replaced by B. So we have three production rules. One start production rule, three non-terminals, S, capital A, capital B, two terminals, A and B, small a and small b, and you want to generate a tree here. So now if you want to generate a tree, you can have, let's say I want to generate a word A, B. Okay. So now in case I want to generate a word A, B, I can either generate a word by this way, or I can generate a word by this way. Both are right. And I am able to generate a tree by these two derivation methods. You can first replace A and then you can replace B, or you can first replace B and then you can replace A non-terminal. So when you have to derive a word more than one way by using a grammar, we will say that this grammar is ambiguous grammar. That machine is confused which way I should use to generate a word, because there is not only one way, there are more than one way to generate a word. So we call that ambiguous grammar. And when we have a grammar where, and by using that grammar, you can generate a word, and there is only one way of generating that word. We can say that this is unambiguous grammar. This is more deterministic. It's unambiguous. Machine is not confused that which method, which path, which derivation method I should use, because there is only one path exists to generate a word. So we always appreciate that we should convert our ambiguous grammar into unambiguous grammar, or we write unambiguous grammar so machine will not be confused. It should be autonomous. It does not require human wisdom, human input to figure out how to do that, what to do that. Okay, so now look at this one. So you have this machine here, you can generate a word, so you can generate this word here. And now look, I give you this example. So we have this grammar here. This grammar is for a star, a plus. Plus is on the exponent, a s s a, and I want to generate three a's. So what I did, I used this production rule. So how many production rules we have? Three production rules, and those three are also start production rules. One non-terminal s, one terminal a there. So I replace this s with as. I reuse this again. S can be replaced by as, and then I use this. S can be replaced by a. And if you see this, I have three a's here. I can use this grammar other way also. I use S can be as, and then S can be SA, this one. And then S can be A. And if you see that, I have three A's there. I have three A's here. I have three A's here. So there are four ways to generate a same word, four different production derivation method, four different parse tree. And for sure, if you have this case, if your grammar has a single word, which can be, your grammar has 1 million words, you can generate with your grammar, let's say 1 million words. And one word, it can be generated by more than one parse tree. The grammar is ambiguous. Okay, your grammar, let's say now I convert this grammar into this one, and now I want to generate three a's. There is no other way other than this. This is the only way to generate 3a in this grammar. This is unambiguous grammar. Okay, so this is your grammar now. That we don't like ambiguous grammar, we always try to create unambiguous grammar. So we will see that how we convert that. So in coming chapters, you will see that when we have a grammar, we will clean that. We will perform some checks, some operations, and then once we convert that, our grammar will be very nice, clean, and readable. So it will be unambiguous at that time. Okay, so now we have, so when you have a total language tree, so you can so you have a grammar, so you completely draw the whole complete tree of your grammar. So let's say you are saying that s can be replaced by, so this 1 2 3, and then this x can be replaced by this. So you try to complete your tree, huh? So make a complete tree for your grammar. And then in your complete tree, if you scan the leaf nodes and you find the same word instance more than one time, like AABB, AABB, it means you can generate this word by using this path or by using this path. It means you can generate this word more than one time, more than one way. So this is ambiguous grammar. This is another check. If you have a, so now if you have a big grammar, you are not able to do that. How you can figure out? You draw the complete binary tree of that, but not binary tree, sorry, complete tree of that, all possible combinations, and then scan the leaf nodes. If you find all leaf nodes are distinct, amazing. This is unambiguous grammar. If you have some duplication of the words in your leaf node, it means this is ambiguous grammar. It can generate one word more than one way. So this is another way you can figure out whether your grammar is ambiguous or unambiguous. Okay, so now look at this one. So here, so sometimes you generate a grammar, the grammar is not good, and you will have a loop there. So S can be replaced by X or B, and X can be replaced by AX, X can be replaced by AX, So now there is no way you can replace this X with anything else. You only have one option, AX. So it is unending operation. So this will be a loop here and machine will be crash. It will be, you will get an error, out of bound error when your stack will be full, because it will never ending process. You will never create a full tree with this grammar. So this is ambiguous grammar. It's not good grammar. So here we finish this chapter. If you guys have any questions, so please you can ask me. We have office hours. I will be available, and please do not forget to do the quiz. And we will start the next chapter in next class. So any question, guys? Let me stop this recording.